there was a question on assignment 1 that included a histogram. It was the ages of the presidents at inauguration. Unfortunately, the chart did not match. I put the wrong chart in, basically what it was. We've used that question before, and I updated the question to answer for 45 presidents, not 44. I updated it. Unfortunately, when I attached the chart, I attached the chart for 44 presidents instead of 45. So what that meant was that the answers would not match the chart that you were trying to interpret them with. Unfortunately, that kind of format question, where it's a fill-in type question, I can't, number one, delete it once people start answering it, and I can't modify it. So I edited the introduction to let you know, don't worry about that. Everybody's going to get full credit for it, no matter what answer you put in there. But you can still look at it and kind of, try and figure out what we were driving at in terms of figuring out the percentages of probabilities and so on. But I'm going to do it with this chart now. I'm going to get a calculator out. Okay, actually, I'm going to use Excel. The reason why I'm going to use Excel is because I can kind of set it up so that you can see me doing my calculations. So they don't quite disappear as dramatically as they would if I just typed into the calculator. Okay, hopefully this will start up soon. It was bouncing, then it stopped bouncing. Now it's not bouncing. Let me try this bit. Is it behind here? Oh, here it is. Okay, came up. Okay, let me increase the size of this thing so we can actually see it. Okay. Okay, I can even go a little bit bigger than that. Let's go to 250. Okay, so this histogram that we're looking at right here describes a sample of a random sample of black cherry trees in, I don't know where they grow black cherry trees. I have a feeling that like cherry trees are, like moderate climates. So maybe Virginia, right? Maryland or Virginia or something like that. So I'm thinking that they're in Maryland or Virginia. And basically this random sample, we're trying to judge what the average height of black cherry trees is in Virginia. So we randomly sampled a number of them, and we can actually count the y-axis.
You hear?
Represents
Can you hear, babe?
The trees in our sample that reach that height, and the x-axis has bins, which represent trees that go from 60 to 64.9 inches.
You can see
65 feet.
The things that he's doing.
Up to 69.
He's talking and he's doing the class like he's on a blackboard at school.
75, 80, and so on and so forth. So, like in all histograms,
okay, babe.
You're right. You're going to be in one of these bins if you're one of the trees that we selected. Oh, okay. Hang on a second. Let me mute. Okay, guys, when you log on, please mute your microphones. Okay, so one of the things that we can judge by looking at this is how many trees did we actually sample here? Well, between 60 and 65 inches, there were 3 trees. There were another 3 between 65 and 70 inches. That's 6. There were 8 from 70 to 75, so that's 6 and 8 is 14. There were 10 in this bin, which is 24, and there's 5 in this bin, which is 29, and we have 2 here, and that's a total of 31. Tell me if I made a mistake there. Okay, so we have 35 trees that we've sampled. Okay, so now our task is to try and interpret this kind of like we would a normal distribution, except that the information is in discrete bins. It's not in a continuous normal distribution. Okay, so for instance, if I asked you where the median is likely to be, which bin is the middle value likely to be? Well, okay, so if we have 31 trees, right? That's an odd number of trees. So the median would be the middle tree, the middle height tree. Okay, so we have 15 and 15 and 1. So that one middle tree would be, we would find that one middle tree by either counting up from the top or counting up from the bottom or counting down from the top. So I'm going to count up from the bottom. So the shortest 3 trees are here. The next 3 short are 6. We got 6. We're here. 6 and 8 is 14 and 15. The 16th tree is going to be in this bin, 75 to 80 inches. So the median tree is going to be somewhere in this bin between 75 and 80 inches. That's simple. We're not looking for anything else more complicated than this. Well, let me take it to the next step. What if I asked you, what's the probability that we would choose if we randomly chose one tree, what's the probability that it would be less than 70 inches tall? Okay, well, these 2 bars represent all the trees that are less than 70 inches tall. So out of 31 trees, we have 6 trees that are less than 31 inches tall. So the probability of randomly selecting a tree that is less than 70 inches tall is going to be 6 divided by 31. Oops. 6 divided by 31. Okay, it's going to be about a little under 20%. It's going to be about 19%. What's the probability that we would randomly select a tree that's over 75 inches tall? Well, we got 10. 10 and 5 is 15, and 2 is 17. So the probability is going to be 17 over 31. Okay, probability that we would randomly select a tree, and that tree would turn out to be more than 75 inches tall, 75 feet tall, is almost 55%. Okay, now there's one other question I might ask about this. The probability of selecting trees under 70 feet was the first one. Under 70 feet. Yeah. Did I do something wrong, or are you just repeating what I wrote? Oh, repeat that, please. Okay, no problem. Yes. The first one was what's the probability of selecting a random tree, and it turned out to be under 70 feet out of the 31 trees that we sampled. Okay, or out of this population of trees, if this is really representative. Okay, now the only other thing that might complicate this is if I impose the condition on this. So for instance, what if I told you that given that a tree is 75 inches tall, what's the probability that it would be greater than 85 inches? Okay, in other words, the probability, right? What's the probability that it would be greater than 85 inches, right? Given, remember that pipe command we used for given that we know that it's greater than 75 inches, 75 feet. Okay, it's kind of tall for a cherry tree, right? I'm not sure where I got this data, but so what's the probability of choosing a tree that's 85 feet tall, given that we know it's 75 feet? So in other words, perhaps we restricted our search to the part of the forest where the trees were all greater than 75 feet or something like that. Okay, so what's that probability? Well, that greater than 75 inches means that we're only considering the trees that are in this bin, this bin, and this bin. In other words, we're only considering 10, 5, 15, and 17 trees. And the probability we're looking for is probability that they would be in this bin. So 2 out of 17 is the probability that we would get that outcome. 2 over 17. Okay, and the unique thing about this is 11% chance that we would select a tree that's greater than 85 feet, given that we're only looking at the ones that are greater than 75 feet. Okay, if that condition wasn't there, if we just want to know what the probability of randomly selecting a tree that's greater than 85 inches, right? What would that probability be? Well, that probability would be, well, there's only 2 trees that size out of 31, 2 over 31. So that probability would only be 6.4% or 0.064. Okay? That's as complicated as this gets. The example in homework was the same deal, except that instead of tree heights, we had ages of presidents, 40 to 45, 45 to 50, et cetera, et cetera. Okay, and it's an example of the same kind of thing. Okay, probability selecting trees under 70 feet was the first one. Yes, under 70 feet. Okay, so that's basically all I'm looking for there. It's not really complicated. It's just the earliest instance where we asked you to consider what a conditional probability looked like. And there's another place where we talked about a conditional probability, and that's when we worked with a contingency table. Okay, here's a contingency table. I'll blow it up so you can see it a little bit better. And in this contingency table, we're looking at a population of 115 people who are gamers. They like playing games on Friday night. They belong to a club. They play games on Friday night. And some of them like playing poker. Some like playing Trivial Pursuit. Some like playing Monopoly. Some like playing Wii Bowling. And each group, has the option of, each one of these people have the option of choosing from 3 desserts that are present: pizza rolls, chips and dip, and cookie. Okay, so what if I were to ask you, what is the probability that if a randomly selected person from these 115 people, what's the probability that that person played poker on Friday night? Well, out of 115 people, 25 of them played poker. So the probability would be 25 over 115. Oops. Okay, so it'd be a little less than 22%. Okay, so what's the probability that they played Monopoly? Well, that's just going to be 38 over 115. Okay, well, what's the probability that they ate pizza rolls that night? Well, 44 people out of 115 ate pizza rolls, right? All it is just basic straight calculations of probability. Well, now let's twist this a little bit and take a look at a conditional probability. What's the probability that they ate pizza rolls given that they played poker? Well, given that they played poker means that had occurred. We know that they had played poker. So we're only considering people that played poker, 25 people. Out of the 25 people, what percentage of them ate pizza rolls? Okay, and that's going to be 10 out of 25. And why are we using 25? Because it's a conditional probability. 40% of the people that played poker ate the pizza rolls. What's the probability that someone played Monopoly and ate chips and dip? Okay, there was no condition there, right? There's just 2 combined probabilities: probability of playing Monopoly, probability of eating chips and dip. There were 17 people out of 115 that satisfied that criteria. So that's equal to 17 out of 125. On the other hand, if I asked you, what's the probability, given that someone played Monopoly, what's the probability that they ate chips and dip? Well, the given that tells us we're only considering the people that played Monopoly, right? That's a precursor to this. And given that they played Monopoly, what's the probability they ate chips and dip? And in that case, that conditional probability now is 17 out of 38. Okay, we all pretty comfortable with that? I think at this by now that should be pretty reasonable. Okay, so let me move on to another topic. Histogram contingency table. Okay, let's see. Okay, so data types. Okay, now I think I reviewed these the last time we were online, and these various data types, I gave you examples of various kinds of data types. I'm going to work from the bottom up. Actually, I work from the top down. I think it's a little bit better. I like that last one as to be the first one. Okay, so the zip code of your local address, right? Your zip code, is that a numerical variable, a categorical or nominal variable, or an ordinal variable? Okay, it's a zip code. It's a number, right? But does that make it really a numerical or scalar variable? Well, the number itself only identifies a location. It's just like saying Brooklyn or Bensonhurst or the South Bronx or something like that, right? So it identifies a location. So even though it's a number, it represents basically a name or a location. So that is a nominal variable, a name. right? Zip code, even though it's numbered, is basically a place, a name for a place. Letter grade you'll receive in this class, A, B, C, and so on. Well, what does that represent? Well, it's kind of looks like a nominal variable, right? Because it's a letter, A, a B, or C. But the thing is that it has a sense of order. It's not on a continuous scale like blood pressure or height or weight or BMI, but it still has order to it. A is greater than B, B is greater than C. So while that's a categorical variable, it's a special class of categorical variable that we call an ordinal variable, right? So country that you were born in, that's pretty clear. That's a name, right? So that is definitely a categorical or nominal variable. Amount of money that you have with you in your pocket right now. Well, that could be, could be anything from $1.15 to $4,323.15 if you just cash the check, right? But that's on a scale, right? From 0 to some large number. So that's going to be a numerical or scalar variable. Miles per gallon your car gets. Again, that's on a scale from 0 miles per gallon to whatever number of miles per gallon. That again is a numerical or scalar variable. The brand of chocolate you prefer, that's a name, right? Nominal variable. The year of your birth, right? They don't use AD anymore, right? They use now modern era or something like that, or current era CE. Anybody know what is it? What's used nowadays? Current era CE, something like that. So it's the same date, right? It's instead of after death, it represents the same date in history, but with a different description, a non-religious description. Okay, so that's a number, right? Year, date, year is a series of numbers. You can actually identify them as numbers or number days. I think that's probably the best way to look at that. Okay. You can even take one date, the other date, subtract one from the other, and see how many days there were in between. The weight of your pet, that's a numerical or scalar variable. The degrees earned by your teachers. Well, unless your teacher has earned 72.5 degrees, and there aren't too many of those, chances are that's a whole number, right? It says earned, in other words, completed degrees, right? So that's a whole number, and it's going to be something that you can reasonably count. So that would be a numerical variable, but a special form of numerical variable, which is a discrete numerical variable. It's an integer and it's a count. It could also be used for, say, number of siblings, 5 siblings, 2 siblings, and so on and so forth. And then finally, we have egg sizes, which are described as small, medium, large, extra large, and jumbo. Okay, now I imagine that there's some way that they sort that. I don't know if it's by size or weight or something like that. But while these are words, they're names or words that represent the relative size of the eggs. What do we know about the size of the eggs? We know jumbo is bigger than extra large is bigger than large is bigger than medium, and medium is bigger than small. Do I know whether one brand's, Purdue eggs, their large is maybe the same size as somebody else's extra large? There's no way for me to know that for sure. It may not be a consistent size, right? But we do know that relative to one another, that these values, while they're names, nominal variables, right? While they're names, they have order, just like grades have order. So these are ordinal variables. Okay, any problem with what I've said so far? Everybody comfortable with this? Okay, we're comfortable. Okay, good. I just take that mean we're comfortable with this. Okay, so now let's take a look. Let's go a little further now, and let's talk about normal distributions. Okay, so I'm going to open up something I can sketch with. Okay, so I'm going to take a population and a variable, a numerical variable that, oops, got this upside down. I'm going to take a numerical variable that I can describe as a normal distribution. Normal distribution is a bell-shaped curve that's symmetrical about the mean. And in this case, I'm going to say mu is equal to 200, and sigma is equal to 15. Okay, and I'm going to say, I don't know what this is. Could be weight or something, weight or some hormone level or test score or something like that. Could be anything. Okay, so sigma is equal to 15, mu is equal to 200. Am I talking about a population or am I talking about a statistic here? Anyone want to hazard a guess? Okay, should be pretty clear right at this stage. Yeah, it's a population, and you know it's a population because I'm using Greek letters because I use that to represent parameters. Parameters are values that describe a population. Okay, if I had used X bar and S for standard deviation, I would have been describing a sample distribution. Okay, so this is a population. Well, there's two ways that we can look. If it's truly a normal distribution, we're making that assumption, then this is symmetrical around the mean. And there's a special relationship between the mean and the standard deviation. Okay, and there's a rule that we have, the empirical rule, that helps us estimate. Okay, the empirical rule helps us estimate that relationship between the mean and the standard deviation. And that relationship tells us that 95% of the people or values or test scores in this population is between 2 standard deviations below the mean and 2 standard deviations above the mean. And it also tells me that if I'm only looking at 1 standard deviation below the mean and 1 standard deviation above the mean, that area represents approximately 68% of this distribution. Okay, well, that's pretty convenient, isn't it? That we know that about these kind of distributions. And while I can describe this in terms of number of standard deviations below and above the mean, we know if the standard deviation is 15 and the mean is 200, for this particular distribution, 1 standard deviation below the mean is going to be 185. And 1 standard deviation above the mean is going to be 215. In other words, 15, 230 for 2 standard deviations above, and 170 for 2 standard deviations below. Okay, and if I were to ask you what percentage of this population has a mean score of, whoops, let me just get back to this. Oh, wrong direction, I think. What percentage of this population has a mean value that's less than 200? Okay, well, less than 200, 200 is the mean. If this is truly symmetrical, then 50% of this population is below 200. Okay, so I can also describe that as 0.5. Okay, the other way I can talk about this is if I asked you, if I selected a random individual, one random individual from this population, what's the probability that their score would be less than 200? And that would be 50%. Since half the people are less than, have scores less than 200, the probability of picking one of those people that are less than 200 is 50%. What if I asked you, what's the probability of picking someone whose score is between 185 and 215? Well, we can recognize that's 1 standard deviation below the mean, 1 standard deviation above the mean. So the probability of picking someone in that range is 68%. Right? Well, how about what's the probability of picking someone that is between 185 and 200? Well, it gets a little bit interesting, doesn't it? Okay, we're talking about this area in here, and that's symmetrical around the mean. This whole area, both sides, one standard deviation below, is 68%. And if it is truly symmetrical, both of these areas that are 1 standard deviation below, mean to 1 standard deviation below, mean to 1 standard deviation above, are equal. So that would be about 34%. Right? This would be 34% of the area of this distribution. This would be 34%. So that would be 0.34. What if I ask you what's the probability of picking someone that's less than 185? Well, less than 185 if this is 34% and everything south of the mean is 50%, 34 less 15, what's left below here is going to be 16% of the distribution, right? 0.16. What's the probability of picking someone that's less than 170? Oh, well, that's interesting. Now, because 170 to 230 represents 95% of the values, right? So that leaves 5% less. Since there's two tails, one at the upper end, one at the bottom end, and they're symmetrical, they're the same size, that 5% that's outside of that range has to be split between them. So that's 2.5% chance of that being true. What's the probability of randomly selecting someone that's greater than 170? Well, that would be everybody that's from here up. Well, since that's only 2.5%, that would leave 0.975, 97.5%. Oops, I'm getting to an area here where it's difficult for me to 0.975. A little difficult for me to write with the graphics tablet. Okay, so yeah, that's why you want the answer in percent. Assume that, yeah, it most likely will give you some sort of hint on how to put it in. For the most part, here in statistics, probably better if you just use, unless I specifically ask for a percentage, to just enter it as a decimal number between 0 and 1. In other words, 0.975, 0.34, 0.68. Okay, unless I specifically ask what's the percentage. Okay, so that's where we stand there. That's the normal distribution. Now, things get a little complicated now. I'm going to take the same distribution and I'm going to redraw it so that we can get a better look at this. Oops. Okay, the mean is 200. The standard deviation is 15. Okay, so now, what if I were to ask you, it was all well and good when we used the empirical rule. When we use the empirical rule, it's all well and good to take a look at this and say, okay, 2 standard deviations is this far, and so on and so forth. But very frequently, we're looking for data that doesn't quite fit the empirical rule. It's not an even number of standard deviations. So let's say I wanted to know what's the probability of randomly selecting someone whose, whatever this number is, weight, for instance, is less than, let me say, 179. Okay, how are we going to figure out what that is? What is that? What is the probability of that occurring? Well, this is 200, and one standard deviation below was 185, and 2 standard was 170. So if I were to look at this, I'd say that would be somewhere around here. And I'm just doing that so I can get a rough idea what it looks like. But the probability randomly selecting someone that has a weight less than 179 or a score less than 179 is the area here below 179. Okay, so I want to know what that area is. Well, fortunately, we have a table that helps us do that. We have the Z table, which describes the standard normal distribution table, which describes for us what these areas are in relation to the number of standard deviations. And here's the Z table. Here we go. So we can take the Z value, the number of standard deviations below the mean, right, which is going to be a negative number because we're to the left. If we were a positive number, we would go with this chart to the right. And this chart shows me that the area that's in these black numbers in here, that area is represented by the gray area here. In other words, whatever the Z-score is that we're going to select, the area that corresponds to it represents the area from that Z-score to the left, everything below that value. Okay, so 179, now I need to know what the Z-score is. Well, had it been 185 we were talking about, the number of standard deviations would have been -1, one standard deviation below the mean. If it had been 170, it would have been -2, 2 standard deviations below the mean. However, in this case, we have a problem. It's not an even number standard deviation, so I need some other mechanism for doing this. So how do I know that's 2 standard deviations below the mean, 170? Well, 170 subtracted from 200 is 30. So it's 2 standard deviations below the mean, 2 times 15 below the mean. It's pretty easy to see there. Well, we're going to do the same thing with 179, except we're going to have to actually calculate it. So the number of standard deviations, we're going to refer to that from now on as the z-score, the z-value of the z-score. So z, in this case, is going to be equal to 179 minus 200, the difference between the mean and that value, over the standard deviation 15. What's that going to be? That's going to be equal to 21 over 15. You actually have to get a calculator out to do that. Where is it? There we go. 21 divided by 15 is equal to 1.4. So that is negative 1.4. Remember, this is negative because I'm subtracting from a larger number. Is equal to negative 1.40. That is our z-score. That's the number of standard deviations below the mean. Now, how do I use that to determine what this area is? Well, I go to my z-table. Okay, where did my z-table go? Let's see. Yeah, I can't scoot up and get everything away here. Okay, 1.40. So the way we use the z-table is we look up the z-score here vertically. So negative 1.4, and negative 1.4 is here. Negative 1.40 is this first number to the right. Had our z-score come out to be negative 1.41, it would have been this next number, which is in the 0.01 column. This represents the third digit, 1.40, 1.4, 1.41, 1.42, 1.43, and so on and so forth. So 1.40 is going to be 0.0808. I think that's what that says, right? I'll blow up a little bit. 1.4. Yep. 0.0808, about 8%, 0.0808. So this area is equal to 0.0808. So the probability of randomly selecting someone from this population that has a score below 179 is about 8%, 0.0808. What's the probability of selecting someone that has a score that's probability that's has a score that's greater than 179, right? Well, greater than 179 is going to be everything to the right of this. Well, that table gives us only what's on to the left, that 8%. So that means if I subtract that from 1, then approximately, I'm not going to figure it out exactly, approximately 92%, 0.90, is this going to be 0.90? It's going to be 0.8992, something like that, right? That almost 90% of this distribution is to the right of that value. Okay. Similarly, I could look up what's the probability of someone having a value that is greater than 200, probability of having a value greater than 206.5, right? What's that probability going to be? Well, let's see. My z-score, again, is going to be 206.5, right? It's going to be somewhere around here. Probability that's going to be greater than that is going to be this area in here. Okay, 206.5 minus 200 over 15 is going to be 6.5 over 15, which is going to be equal to, let me get a calculator again. Is going to be equal to 0.433, 0.433. That's going to be positive, plus 0.433. Okay, that's our z-score, right, that we're interested in. Well, what area does that represent? Okay, let's go to our z-table, go to the positive side this time. 0.04, and what was it again? 0.433, 0.043. Okay, so that's the next day. We only get 3 significant digits, 043, 0.043, 041, 040, 041, 042, 043, 044. Okay, 043 rather is 0.6664. 0.66 0.6664. Only problem is this table gives us the area to the left of that z-score value. So we're not going to get directly from that table the area to the right. We're going to get the area from here down, right? And what's going to be left here, 1 minus 0.6664, is going to be what that area represents. Okay, let's go ahead and do that. Okay, let me clear this out. So 1 minus 0.6664 is equal to about 33%, or 0.3336. That would represent now 0.3336, right? That's what that area represents. Now, what if I asked you, what's the probability that you would randomly choose someone whose score weight is between 179 and 200, right? I'm sorry, not 200, 206.5. Well, where's that area? That area is going to be the area between the two that we just determined. Okay, that area is going to be in there. So that's 179 to 206.5. Well, what is that area? Well, that area is going to be, the only thing that is excluded from that area is this area below 179 and this area above 206.5. So that's going to be 1 minus the sum of 0.0808 and 0.3336, right? So it's whatever's left after we add these two together, subtract it from 1, that'll leave us with the area that's between the two. I try not to round until I'm completely done, if I possibly can. And usually, to tell you the truth, usually I would use Excel to solve this. I'm trying to be a little bit more transparent by using the calculator. I would normally use Excel, and Excel remembers all the, even if you have the formatting rounded to only show 2 decimal places, Excel keeps all the decimal places when it makes subsequent calculations. You ever around when you get the z-score and you just take the 2 decimal point? Well, on the z table that we have here, you can only have up to 3 significant digits for the z-score. So you have to round there. You have to choose which z-score, which area you're going to pick for that. Okay, so let's figure out. Let me just figure out what that is. 0.0808 plus 0.3336 is equal to this, and I'm gonna rather than flip the signs, I'm just gonna subtract 1. So I subtract 1 from that. 0.5856 is the area that's between the two of these. Okay, so that's basically what we're dealing with there. That's a normal distribution. Okay, so next, let me do another example here. Okay, next, I'm going to turn this around a little bit more. And I'm going to tell you that we're going to take from that same population, mu is equal to 200, sigma is equal to 15. Okay, we're now going to take this, now going to take that population, and we're going to take a sample from that population. And that sample, the sample size that we take from that population is going to be equal to, let's see, is equal to 25, right? Okay, sample size is 25. So I'm going to draw what is the distribution of repeated samples of size 25 from this population. What would it look like? Well, what it would look like is, number one, the mean of those repeated samples would be the same as the population, or approximate the same as the population. So the mean would be 200. But the standard deviation, the spread, would no longer be 15, because we're taking 25 scores, averaging them, and then doing it again, taking 24, averaging them. So they're not going to be as variable as the individual scores are. So what is the standard deviation of this plot of repeated samples of size 25 going to look like? Well, the standard deviation is going to be equal to the standard deviation of the population over the square root of the sample size. Well, to avoid confusion, when we're talking about a sample distribution, we call this the standard error instead of the standard deviation. Instead of the standard deviation, we refer to it as a standard error. So if I were to ask you, this distribution now has a standard error that's equal to 15 divided by the square root of 25, which is 5. It's equal to 3. So now I would ask you, if I took a sample, a new sample of sample size 25, what's the probability that the mean of that sample of 25 would be less than 190? What's the probability that that would occur? We do exactly the same thing. Here's 190. Actually, it's 3 standard deviations, so 190 is probably going to wind up down here. So this is a much narrower distribution than the original populations. That 190 is going to be down there. What's the z-score going to be? Z-score is going to be equal to 190 minus 200 over the standard error, which is 3. That's going to be 10 over 3 is going to be equal to 3.33. That's our z-score. What do I do to find the area that represents probability of getting sample size 25 and having a mean below 190? For that sample, let's go to our standard deviation. Let's go to our z-table to calculate that. And that's going to be negative 3.33. 0, 1, 2, 3 is going to be 0.00004. So this area is going to be quite small. It's going to be 0.0004. So this would be 1%. This would be 4%. This would be 0.4%. This is 4/100% is the probability or probability of 0.0004 of getting that result. Is it impossible to get that result? No, but it's very unlikely that we would get a result that small. But that's what it comes out to be. I just want to go back and do one other thing with the original normal distribution that we were looking at. And that is, I'm going to draw it again. And that is, I'll sketch it out here. Okay. Okay, I'm going to go back to our original population. Mu is equal to 200. Sigma is equal to 15. What if I asked you, what is the value above which 10% of this population resides? Right? In other words, let's say that this represents people's weights. Or, let's say it represents people's weights. And we say, we want to interview, or we want to do some sort of intervention, or we want to re-examine. You could be 200 pounds and be fit as a fiddle, right? But we want to check on that. We want to re-examine or call back people whose weight is in the top 10% of this population. We don't want to interview everybody. We only want the people that are in the top 10%. So I know the mean is 200. I know the standard deviation is 15, but what weight represents the top 10%? In other words, what is this value for weight that I get if I'm looking at this area, which represents 10%, 0.10, that area right there? Well, I need now to figure out what is the z-score of this value x. What z-score is that would give me 10% of the population to the right of that? In other words, 90% of the population is below it, only 10% of the population is above it. So let's go to our z-table again and see if we can't get some help with that. Okay, there's our z-table. I'll pull it up. There's our z-table, and we're on the right side, so we're using the positive one. So this time I'm going to use it backwards. I'm going to look for the area, the shaded area, the z-score for the shaded area that represents 90% to the left. So let's look for 90% in here. Kind of dig around here. 89%, 89.4, 89.8, 0.8997. That's the closest one right there. What does it come out to be? That comes out to be a z-score of 1.28. So this value for x happens to be where the z-score is equal to plus 1.28, I think it was, right? 1.28. So I need to figure out what value that has for this distribution. Well, remember we were using the z-score. The way we're using the z-score is we were subtracting the value we're interested in, x, minus the mean divided by the standard deviation, right? So in this case, before we knew what x is, we knew what mu, what the mean was, we knew what standard deviation was, we used to calculate z. This time we know what z is, and we know what mu is, right? And we know what sigma is, but the only thing that's left that we don't know is x. Since there's only an unknown formula, we can now calculate what x has to be to represent a z-score of 1.28. So it's going to be 1.28, and I'm going to multiply by 15 on both sides, so I get rid of that division, is equal to x minus 200. And now x is equal to, I'm going to move 200 to the other side, 200 plus 1.28 times 15. Okay, and I'll work that out now. I'll get my calculator out again. Okay, so the first thing I'm going to do, I'm going to clear this out. So 1.28 times 15 is equal to this plus 200. So that value is 219.2. So I know that anyone who weighs more than 219.2 is in the top 10% of weights for this population. Okay, so you can manipulate this. You use this a number of different ways. Okay, so let's move on to another calculation. Okay, let's move on to confidence intervals. Okay, now let's see. So the central limit theorem that we learned about in class tells us how samples are distributed. And since we have an understanding how samples and standard deviations behave, we can now use them to help us understand how well we know the actual value of the population mean. Unfortunately, we'll never know it for sure because we never really, the population mean exists, it's a real number, but we just don't have a way to actually know what it is for sure without actually sampling everybody, measuring everybody. So that usually is not very convenient. I'm going to start out with the assumption that we don't know what the mean is, but we do know that the standard deviation is equal to 15. Okay, so the central limit theorem tells us that repeated samples of size n, we take repeated samples from this population of size n, then the standard error of your repeated samples is going to be, in other words, your new distribution made up from repeating the samples over and over again, is going to be equal to the standard deviation of the population over the square root of the sample size. So let's say I'm taking samples of size, you know, I'm using a graphics tablet and it doesn't like sweaty hands, and I don't have the air conditioning on in this room, so my hands are a little bit damp, and it really doesn't like it. I'm gonna close this and reopen this so we can see this a little bit better. Okay. Normally it'll ignore my palm resting on it, but I'm having a little bit of trouble with that right now. Okay, so our standard error, mu is unknown. Okay, and sigma we know is equal to 15. Usually we won't know sigma, but for the moment I'm going to assume that we know sigma. So we take a sample of size, I don't remember what I said, say size 25. We know sigma. So we know that the way that repeated samples are going to be distributed in this population, if we take samples of size 25 over and over again, the means are going to be distributed normally, and they are going to have a standard error or standard deviation of the repeated means that's equal to sigma over the square root of the sample size, right? Which is going to be equal to 25. It's going to be equal to, excuse me, 15 over the square root of 25, which is 5. So that's going to be 15 over 5 is going to be equal to 3. That's our new standard error. And we also know then that if I take a sample of size 25 from this population, and my sample, my X bar, comes up, let's say 195, right? I can calculate a confidence interval around that sample mean that'll tell me with whatever level of confidence I want, either 95, 99, or 90% level of confidence. It'll tell me that level, with that level of confidence, it'll tell me what range within numbers around 195, what range of numbers around 95 that I would need to be able to predict that the true mean, mu, is between those two numbers, 95% certainty, 99% certainty, and so on. And the way we calculate that, we take our sample mean and we add and subtract 1.96. What does 1.96 represent? 1.96 represents the actual value for 2 standard deviations below and 2 standard deviations above. In reality, if you look at the Z table, the point at which you have 2.5% in the lower tail and 2.5% in the upper tail is when you're not exactly 2, but actually 1.9 standard deviations below and above the mean. So I'm going to use the actual value now, 1.96, times our standard error. And that is for a 95% confidence interval. So X bar in this case is 195. Okay, plus or minus 1.96 times the standard error, which is 3. Okay, now for my purposes, you should multiply this out and actually get the real number. My purposes, I'm just going to use 2. It's going to be plus or minus 2, 195, plus or minus 2. I'm sorry, plus or minus 6, right? When I'm using 2, so it's going to be plus or minus 6. So my confidence interval is going to be 6 subtracted 189, 6 added to that is going to be 201. So I am 95% confident that the true mean lies between 189 and 201. Well, in fact, if this is the same distribution we looked at before and it's secretly 200, we achieve that. 200 is between those two numbers. Okay, if I want to be 99% certain, instead of using 1.96, I would use, anyone want to tell me what I would use? You should know by now, right? What would I use instead of 1.96? Right? I would use 2.58, exactly 2.58 times our standard error. And if I wanted to be, if I were willing to be, and what is this going to be, wider or narrower than this range? Is it going to be wider range or a narrower range? Anybody want to hazard a guess there? If I'm multiplying by a bigger number and adding and subtracting, right, that's going to be a bigger number. Now that's 2.5 times 3. So that's more like adding 2 times 3 is 6. 2.5 times 3 is 6, and 1.5 is 7.5. So I'm adding and subtracting 7.5 from 195. So that would be 187.5 to 7.5 above to 202.5. Right, that's going to be my confidence interval here. So our 99% confidence interval turns out to be wider than our 95% confidence interval. That makes sense. If I make those two numbers further apart, I am more certain that the true mean is going to be between these two numbers somewhere. If I make them narrower, then I'm less confident. So in other words, a 95% confidence interval is narrower than the 99% confidence interval for that reason. And if I use 90%, I was satisfied with 90% certain, I can make it even narrower than that. In that case, it would be 195 plus or minus 1.64 instead of 2.58. Okay, so remember those numbers, 2.58, 1.64, and especially 1.96, because that's most of the time you're going to be using that. Okay, so now to add a special curve into this thing, let's say, I told you what sigma was, right? Let's say we have a population and mu, and with sigma, okay, secretly it's 215. It's the same one we were working with before. But we don't know that. We don't know what the mean is. We don't know what the standard deviation is for the population. All we know is we took a sample of size 25. That's a relatively small sample. Okay, so our sample is size 25. Our mean comes out to be X bar is equal to 197. And our standard deviation for those 25 values turns out to be let's see, our standard deviation for those values turns out to be 16. Okay. So the mean approximates the mean of the population. The standard deviation or variability of the sample approximates the standard deviation, sigma, of the population. It's not exactly the same. And before, when we knew sigma, the only thing that was very variable, the only thing we were guessing at, is whether or not X bar really was close to what the mean was. But now we don't know what sigma is, so now we have additional uncertainty we have to deal with. So instead of using the Z table, we use a new statistic, a new value called the T statistic. And that T statistic it winds up being a large, based on sample size, it winds up being a larger number than the T statistic. And that larger number means we're going to get a wider confidence interval, and it's going to make up for that extra level of uncertainty. So let's see how we would calculate the confidence interval here. I would say X bar plus or minus, and this is for a 95% confidence interval, right? X bar plus or minus. Now I would not use 1.96 because this is a relatively small sample, and I can only use 1.96 if it's a small sample. If it's a small sample, I can only use it if I know the population standard deviation. For sure, I don't know. So I have to use the T value that represents 95% confidence, right? A lot of times they'll represent that alpha error is 0.05. In other words, if you're 95% confident, you have a 5% chance of being wrong. Okay, and a lot of times down here to signify that that's what you're after, they will put alpha over 2 is equal to 0.025, right? So alpha over 2, right, is equal to 0.025, comma, and degrees of freedom. Okay, degrees of freedom is just another way of saying the sample size, except degrees of freedom is just the sample size minus 1. So we want the T-score that represents 95% confidence or 5% chance of being wrong, and the sample size, which represents the n minus 1, in this case, degrees of freedom, times the standard error. Okay, so we're using that number in place of 1.96. Why are we using it? Because we don't know what sigma is, and we're dealing with a small sample. I would perhaps suggest a large sample might be something like 50, 100, something like that. In which case, there'll be a bit of error introduced, but you might consider using 1.96 if you had, say, a sample size of 100. But you can't go wrong if you're depending on the sample for your standard deviation instead of the population. Well, then you can't go wrong by using the T-score for any value, even for a big value. So it's going to be a little bit more accurate. Okay, so let's see what this is going to be in this case. So X bar is going to be 197 plus or minus the T value, which I'm going to look up, times our standard error. And what's our standard error going to be equal to? Our standard error is equal to sigma over the square root of n. We don't know what sigma is, so we're going to use our best estimate of it, which is our standard deviation for a sample, over the square root of the sample size, which is 25. That's going to be, what was I here? Sigma is equal to 16 over 25. 16 over 5 is equal to, it's equal to 3.2, right? Yeah, 3.2. That is what our standard error is in this case. So the standard error is going to be equal to 3.2. But now we have to figure out what the T-score has to be, what the T value has to be. So we go to our T table. There's one in your book. You can use the one that I frequently use that's on Blackboard in several places. From this manual T table. If I can't get to it quickly. Okay, here it is. And we open it, and there we go. Okay, I'll drag it open here. Okay, so I'm going to have to look for the T value that I need. And let's see how I find it here. This column represents the degrees of freedom, which to us is basically the sample size, minus 1. So our sample size is 25. So we're going to go down to 24 for our degrees of freedom to find out our T-score. And the column that we're going to choose for our T-score, a T value, is going to be the one for 95% confidence interval. In other words, alpha over 2, that 2.5% in each one of the tails left and right, corresponds to a 95% confidence interval. So I'm going to scroll down here in this column until I get to the value for 24, and it's 2.064. So instead of putting in 1.96 here, I put 2.064. And I multiply these two out. Okay, I'm going to say 2.064 times 3.2 is equal to 6.60. I'm going to call it 6.0. I'm just going to call it 6.6. Okay, for our purposes. Normally, I would keep all those digits until I'm all done, right? After I do the adding and subtracting and multiplying, I would keep all those digits. But just for expediency, I'm just going to keep the 6.6. So 197 plus or minus 6.6. Okay, now I didn't mention this up. I mentioned it in some of the videos, but anybody know what the name for this quantity after you resolve this, multiply the p-value or the z-score, it doesn't matter which one, times the standard error, that value, what that value that we're adding and subtracting is called? Anybody recall that? That's the margin of error. Exactly. That value is the margin of error, the plus or minus for our confidence interval. So our confidence interval now is going to be 203.6, and going the other direction, 6 less is going to be 190.4. And that's going to be our 95% confidence interval for this sample that we have. We're 95% sure the true mean is between these two values. Okay, so, and I think if you get that basic, you get this kind of under your belt, you can start to understand how we use the normal distribution, how we use the central limit theorem to produce these confidence intervals. I want to bring up one other confidence interval that we might want to calculate, and that's when we're dealing with a proportions. Okay, and we have a special method of dealing with them. Okay, so let's say that let's say I want to know what is the proportion of people in this population that voted in the last election. Okay, so I don't have access to polling day, or let's say I'm going to vote in this coming election. So we would go out and we would survey a number of people. Usually when you do that kind of survey, you're not surveying 25 people. You're surveying a large number of people. Let's say in this case, our sample size is going to be 400 people. Okay, and let's say it turns out that out of those 400 people, right, adults over 18, out of those 400 people, that 230 of them say yes, I plan on voting in November, and the remainder of them say no, or they're not committal, right? So what is the proportion of people in this sample that say they're voting? Well, it's 230 out of 400. And what is that percentage? Let's calculate that percentage. That percentage is going to be 230 divided by 400 is equal to 0.575. So P is equal to 57.5%, 0.575. Okay, now the only thing is that that's not really P, is it? P is the population proportion of all the voters in New York City. What percentage of them are going to vote? Well, that's the population proportion. We don't know that. We're not going to know that until November, and that's only if we count every vote and we add up and count all the people that actually voted, not just percentages, right? So we don't know what P is going to be, right? We don't know what P is, as how the whole population would have answered this question, because we didn't ask the whole population. We only asked 400 people out of the whole population. So we don't know what P, just like we don't know what mu is. Both of these are point estimates for the middle of a distribution, right? So we don't know what P is, and we don't know what mu is, right? So how can I, again, quantify how well I know what P is? And first of all, instead of calling it P, just like I used X bar for the mean, I'm going to use P cap to represent the proportion of a sample instead of the proportion of the population. So this is what I got for my sample. And just like my sample, I can set up a confidence interval. P cap plus or minus, okay, now I'm going to put in whatever score is going to be there, times my standard error. Well, what's going to go in here? What's going to go in here is 1.96. Well, wait a minute, Tony. All your information is from a sample. You don't know the population proportion. How do you justify putting in 1.96? Well, I justify it because the sample size that I'm using with proportions is typically going to be a very large sample. And I know from my t-table that when I'm dealing with a very large sample, as the sample size increases, like look, it's for 18 degrees of freedom, 2.1, 2.07, 2.04, 2.0, 1.98, 1.98. Look, at 100, a sample size of 100, it's already very, very close to 1.96. As the sample size gets larger, it approximates it gets closer and closer to 1.96. So with a big sample like 400 or 1,000 or several thousand, I feel pretty comfortable using 1.96 instead of another p-value. Okay, so now I just need to put in a p-value, which is 0.575 plus or minus 1.96 times our standard error. How do I calculate standard error for proportion? Well, I think we gave you this formula, right? Standard error is equal to, for repeated samples of size 400, is going to be equal to the square root of p times 1 minus p. Of course, we know what p is, so we use p cap for this formula, over the sample size. Right? So what is that equal to? That's equal to the square root of 0.575 times 0.425 over the sample size, which is 400. Okay, let's work that out. Let me get my calculator. Okay, that's going to be 0.575 times 0.425. And that's what this is equal to. Divided by 400 equals this. We take the square root of that, and our standard error for this proportion, repeated samples of size 100, is 0.0247. Now, I would, if I could, I would use Excel, keep this whole number, but I would at least keep 0.0247 so that you could, you have at least some extra digits here when you do your calculation. And then at the very end, if you really want to round down to maybe three significant digits or something like that. Okay, so 0.0247, from our purposes, I'm going to say 0.025, right? But not you, 0.025. Okay, standard error is 0.025, 0.025. Let's see what I'm going to get here. 0.575 plus or minus 1.96 times 0.025. Okay, well, I'm gonna again, you're not gonna do this. I'm gonna say 2 times this is gonna be plus or minus, right? Plus or minus 2.5% times 2 is 5%, 0.05. So our 95% confidence interval is going to be 0.575 minus 0.05 is going to be 0.525, and plus 0.05 is going to be 0.625, right? So we're 95% sure that our sample came out to give us a proportion of 0.575. We're 95% sure based on that our 95% confidence interval, that our true mean, we're 95% certain that our true mean, that true value of P for everybody, had we sampled the entire population, would be between 52.5% to 62.5%, 0.525 and 0.625. Okay, I'm going to do one more thing. I'm going to do one more thing now, okay? And that's going to be, I'm going to talk about now the binomial distribution, okay? So let's do a simple question on the binomial distribution. Okay, so let's say that the probability that let's see, the percentage of people in New York City, the percentage of people in New York City that ride a bicycle to work on a regular basis, I'm going to make up a number, is 20%. They put in these bike lanes on Queens Boulevard, so took away 1 million parking spaces and stuff like that. So there's a big uproar in Queens because they put in these bicycle lanes, but there's like one bicycle on them every half hour, so they're not exactly getting used a lot. So it's causing a lot of controversy. But I'm going to make this up anyway and say 20% of the population bikes to work on a regular basis. Maybe this might be more like Amsterdam or something like that, right? Some European city than New York. But I'm gonna start with that. Maybe that'll happen in the future for all we know, right? Okay. So the probability, if I randomly select someone in the age range of 20 to 40 or something like that, the probability that that person would be a person that bikes to work on a regular basis is 20%. That's basically what I'm saying here. Now, what if I told you I'm going to randomly select 10 people that are between 20 and 40 years old in New York City, that same population, and I'm going to ask you, what's the probability that out of those 10 people, exactly 2 out of those 10 people bike to work every day, bike to work on a regular basis? Exactly 2. What's that probability? Well, that's where the binomial distribution comes in, because out of those 10, each one of those 10 people could have 2 values, yes or no, success or not success. Success being that you identified a person that actually bikes to work. So let's see what that probability would be for this situation. So to do that, we use the binomial distribution function. We went over a bit of this in class. So that function works like this: equals binom dist, parentheses. Once you put the parentheses in, it prompts you to tell it the information that it needs at that point. So the first thing it needs is a number of successes. So I said we want to know, out of 10 people, what's the probability exactly 2 people out of our sample of 10 people bike to work on a regular basis. So the number of successes that we're looking for is 2. And the number of trials, in other words, the sample size, is 10. So we're saying what exactly is the probability that I'll get exactly 2 out of 10 that bike to work every day. I'm going to put another comment here. The next thing it wants to know is the probability for any individual. If I randomly picked any person in this population, probability that they bike to work is, as we said, 20%. And then comma, and then it's asked me for cumulative, and it's asking me to tell it true or false. If I say true, it's going to give me the probability for 2, 1, and 0. In other words, a probability of 2 or fewer people out of 10 that are that bike to work on a regular basis. That's not the question answer. The question answer was the probability of exactly 2 out of 10. So I say false. I don't want it to be cumulative. I just want that one specific outcome. And that probability is 30%. There's a 30% chance that if you sample 10 people, that 2 out of the 10 would tell you that they bike to work on a regular basis. Well, let's say if I had asked you the other thing I mentioned to you, what's the probability that 2 or fewer? In other words, what satisfies you now? 2 out of 10 satisfies you, 1 out of 10 satisfies you, 0 out of 10 satisfies you. So this time, I'm going to put in exactly the same thing. Parentheses, and this time its number of successes is 2, comma, trials is 10, our sample size, comma, 0.2 is the probability of any individual biking to work on a regular basis. So this time I'm going to put in true for cumulative. So that means it's going to give me the sum of a probability for 2, 1, and 0. In that case, it's a 68% probability that you would get that person out of the 10 people. You would get either 2 out of 10, 1 out of 10, or 0 out of 10. That would tell you that they bike on a regular basis. Okay, so and you could if you parse the question, what if I ask you what's the probability that more than 2 people, you would get more than 2 people out of 10? Well, that tells you that you want to exclude 2, 1, and 0, but you want the probability for everything else that's left, right? So in that case, we know the probability for 2, 0, and 1 is 0.677. The probability for more than 2 is going to be 1 minus the probability for 2, 0, and 1. It's going to be 32%. And what if I ask you, what's the probability of more than one person biking to work, right? Well, the probability of more than one person, that means 2, 3, 4, you take that sample of 10 people and you get either 2 out of 10, 3 out of 10, 4 out of 10, all of those. So I'm going to trick this. I'm going to say the binomial distribution probability of more than one person, binom dist, parentheses, I'm going to put in 1 for successes, 10, comma, 0.2, comma, and true, and that would give me the probability for 1 and 0. And since I asked for what's the probability of more than one person out of 10, in other words, 2 and up would satisfy this, it's going to be equal to 1 minus the probability for just 1 and 0. Whoops, I didn't put an equal sign in there. I did put an equal sign in there. 1 minus this value. And that's the probability for 2 or more percent. More than 1 is the same way as saying 2 or more, right? In either case, that's how you would solve that particular problem. Okay, I think we've covered most of what I think people were having issues with. I just want to do one more thing. Somebody mentioned some homework problems on 3B, and I want to take a quick look at them to see what kind of homework problems they were. Assignment 3B, central limit theorem, and which ones were they? They were 4, 5, 6, 11, and 12. I may not get to all of them, but I think I can kind of explain them at least anyway. Okay, so let's go to 4. Okay, well, 4 is not really a question by itself. Among adults in the United States, the distribution of albumin levels, we have a lot of good stuff, is the population mean is 29.5 and the standard deviation is 9.25. Sigma and mu, so we're talking about population. Suppose you select repeated samples of size 20 from this population. Calculate the mean for each sample. What would you expect the mean of this? You do it repeatedly, calculate all means. What do you expect the mean of this sample to be? Well, if we take repeated samples of size 20, we would expect that our samples are going to have a mean that's similar to the population mean. That's why we take samples. So the average we would expect would be the same as 29.5, the same as the population mean. What would you expect the standard deviation for the repeated sample means to be? Well, our new sample distribution, even though it's going to approximate the population mean, it's going to be a tighter cluster of values because their samples are size 20. So it's going to be the standard deviation of the population, 9.25, divided by the square root of the sample size, which is the square root of 20. What's another name for the standard deviation of sample means? Didn't we just mention that? Standard error. Okay. What proportion of the means of a size 20 are expected to be larger than 33 milligrams? We did something very similar to that just now, didn't we? Okay, so in other words, our new sample distribution, based on central limit, our new sample distribution has the same mean as the population, 29.5, but its standard deviation is 9.25 divided by the square root of 20. So I'm going to take a wild guess and say square root of 20 is 5, a little bit more than 4, less than 5. So I'm going to say let's say that it's 2, just for argument's sake. The standard error is 9.25 divided by the square root of 20. Let's say that comes out to be 2, just to make things simple. So now we're asking about a distribution of sample means where the mean is 29.5 with a standard error of 2. So how many standard deviations away from 29.5 is the value 33? So 33 minus 29.5 is going to be 3.5, right? Over the standard error, which is 2. So that's a little less than 2 standard deviations. And we can use our z-table to look up what area is above a z-score of, say, whatever it comes out to, say, 1.9 or something like that. What proportion of the sample means are expected to be less than 28? Well, 28 minus 29.5 over 2 would give you this, approximately 2 would give you the z-score. It's a negative number this time. 28 minus 29.5 is 1.5 divided by 2 is about 3/4. Negative 0.75. Again, it's just a real rough estimate. Negative 0.75 z-score. And you will go to the z-table, look up that z-score, and see what area, what proportion of that sample distribution is going to be below that, and then what proportion is between 28 and 33. And that's, if you draw this, if you sketch this out now, you've calculated the area below 28 and the area above 33. So what's left in the middle? What's left in the middle is whatever isn't on the outside, the area below 28, the area above 33, add them together and subtract it from 1. That'll give you the area in the middle. Okay, 11. Okay. As above and above, the probability an infant is born prematurely in Mexico is 0.15, 15%. We would expect 95% of the proportions of sample size 625 to be between this value and that value. Okay, so let's say you take a sample of size 625 and 15% of the infants are born prematurely. Let's say an error. Oh, well, in fact, you could use the result from this. Probability infant is born prematurely in Mexico is 15%. What is the standard error for the proportion of premature developers for repeated samples in its population? Oh, you know what it is? That's 2 different questions. I don't know if I meant to put 25 in there or it's actually 2 different questions, but that's a different answer. That'd be the square root of 25. This is a sample size of 625. Right? In this case, you knew what the actual proportion was. It's given to you. You know what P is. In this case, you know what P is. You take a sample of 625. So now our 95% confidence interval. Our 95% confidence interval is going to be P cap, which is 0.15, plus or minus 1.96, because it's a big sample. 1.96 times the standard error. How do we get standard error? Standard error is 0.15 times 0.85 over 625, and we take the square root of the whole thing. Same formula that we used before. And this is the lower end. That's the upper end of the confidence interval. This is the lower end of the confidence interval. We take our margin of error, add it to 0.15, take our margin of error, and subtract it, or the other way around, whichever one it happens to be. Okay, so I think that should help out a bit, I hope. And it recorded. I hope the whole session recorded. So hopefully we'll be in pretty good shape this time for me and able to post it. And good luck on the test. Work on it. Use it as a learning exercise. Okay, we're gonna have to try and keep up with the sessions we still have going. Yesterday, what I'm going to post on Wednesday and what I'm going to post on Friday, because towards the beginning of next week, after the beginning of next week, maybe midweek, I'll have to post the second exam. Fortunately, the second exam will only cover the new material. It won't cover the stuff that was on exam 1 already. Okay, and that, if you wind up doing a project, that's the last exam you're going to have to take, and we'll figure out how to deal with the projects once I post exam 2. But you can choose to take exam 3 that will cover only the couple of things that we do beyond exam 2 towards the end of the semester. And it's really needs you guys to buckle down, because this is such a, I mean, we're halfway through the semester and we're only about 2.5 weeks in, right? So it's brutal doing this in 5 weeks. I understand that and I sympathize, but it's incumbent on you guys to try and keep up as best you can. On the other hand, look at it this way. You get to do something you would have to spend a whole semester doing in 5 weeks. So that's got to have some value for you. And instead of spending 2 months of your summer taking this in 8 weeks, you were able to get it done in basically just a week more than a month, right? So there is a trade-off there, but it requires you to really kind of buckle down and do what you need to, spend the time that you need to do, and just tough out these 5 weeks, you know, so that you can get through this, and hopefully, you know, hopefully you'll remember a little of it too. I'd be ecstatic if you actually remembered any of this stuff as well. So in this week, we're going to be covering some more, some statistical tests, the t-test, the chi-square test, odds ratio, analysis of variance. They sound intimidating, but functionally, when you apply them, it doesn't have to be that intimidating when you actually apply them. And for a lot of the application of them, we're going to be using SPSS. And SPSS will literally help walk you through practically how to apply them correctly. You just have to make sure you're selecting the correct test for the type of variables that you're working with. And we'll be working on that as we move forward. Okay, so good luck, and I'll talk to you guys again soon. Bye.